So this video is on applications of exponential and logarithmic functions. Now, you can see that the simplest application is a compound interest, where the formula is A is equal to P times 1 plus R over N raised N T. N is the number of times the interest rate is applied, R is the rate, usually in percentage, and T is the term of the loan. Now, for a loan, the formula here, the compound interest formula, gives you the total amount including principal and interest. If you want to find the interest, you subtract the principal from the amount using this simple expression. But if it's an investment scenario, the same formula would give you a future value. It's just a matter of terminology. Now, if the interest is applied continuously, then the final amount is given by P times E raised RT. So this entire block gets changed by E raised RT. It becomes an exponential equation. An easy way to remember this is to think of per deodorant. Now, here is an example. Suppose you borrow a loan of $5,000 at a 2% annual rate, applied semi-annually for a period of 6 years. What is the value of the compound interest? Now, the second part, what is the interest if the rate is applied continuously? The given information is the principal is 5,000, the rate is 0.02, T is 6, and N is 2. The number of times the rate is applied, and we get that information by looking at the term semi-annually. If it said quarterly, then N would be 4. If it said monthly, then N would be 12. So what I have to do is take these values that are provided and plug it in my compound interest formula. So when I plug it in, I end up getting 5,000 times 1.01 raised 12. That gives me an approximate amount of 5,625. Keep in mind that is amount plus interest. If you want to find interest, you subtract the principal, which is the 5,000 that you had initially, from 5,625. You'd end up getting an interest of 625. Part B, if you want to apply the rate continuously, the formula changes to P E raised RT. Now, again, I'm plugging in the values of 5,000. E raised R is 0.02 and T is 6. And when I plug in and solve, I end up getting an answer of 5,635. And again, this is the total amount, which includes the amount in the principal. If you want the interest alone, you subtract the principal of 5,000 from it, so the interest turns out to be 635. So what does this tell us? This tells us the maximum amount of interest in this scenario when you get $5,000 at a rate of 0.02% for a term of 6 years. The maximum interest you will owe would be 635. Could it be less? Yes, it could be less, but it could never exceed by changing the number of times you apply the interest. So the maximum interest that you would owe in this scenario, based on the given value of R, based on the given value of T and P, would be $635. And that's why continuous compound interest is more applicable than just the compound interest formula. Now, extending the idea of compound interest, if we change the formula, we end up getting two different models. One is the growth model, the other is the decay model. You can see the difference between the two is just a negative sign. Here, A is the final amount, A naught is the initial amount, R is the rate, and T is the time. In an exponential growth model, you start with an initial amount A naught and that initial amount grows at a rate of r for a period t, and this formula would give you the final amount at time t. In a decay model, you start with an initial amount a naught, the amount decays at a rate of r, and over time t, and at time t, you have a final amount of a. So with the growth model, an important quantity is the doubling time, which is given by the simple formula natural logarithm of 2 divided by r. The half-life time has the same formula, interestingly. So here's an example. Suppose a petri dish has 10 bacteria, which is known to grow exponentially at a rate of 0.12 per hour. What is the number of bacteria at 3 hours? What is the doubling time? So I start with 10 bacteria. R is 0.12. A is a naught, the initial value, and I plug in the rate, which is 0.12, and T is 3 hours, because I would like to know the quantity at 3 hours. So when I plug it in and use a calculator, I find the answer to be 14.33. So the amount turns out to be 14 bacteria at 3 hours. Now, the doubling time would mean the time when I would have 20 bacteria. At 3 hours, I had about 14 bacteria, which would mean in a growing model, 20 bacteria would happen at a time greater than 3. And when I plug it in the formula, clearly I find that answer to be 5.77 hours. It's quite simple, natural logarithm of 2 divided by the given rate. This example is on a half-life model. So suppose you start with 100 milligrams of drug in the system, and if the drug decays at a rate of 0.07 milligrams per hour, what is the amount of the drug in the system at time t equals 4 hours, and what is the half-life of the drug? Keep in mind, you cannot have a doubling time for a decay model. You cannot have a half-life time for a growth model. It is very intuitive. Think about it. So I use the expression for the decay model, and I plug in the given rate of 0.07 and the initial amount to 400 and the time for. I find that at 4 hours the final amount would be 75.57 milligrams. So if I want to know the time when the drug would become exactly half of what you started with, and there was 50 milligrams, you can find that by using this formula, natural logarithm of 2 divided by 0.07, which is 9.902 hours, which is approximately 10 hours. Here is another formula, or another example, which kind of does things backwards. Suppose you have an amount of 700 bacteria at some time t, and you know the bacteria grows exponentially at a rate of 0.02 per hour, and you know that initially it was at 400, and we want to know the time when it became 700. So the final amount is given, the initial amount is given, the rate is given, but the time is not. So we're actually solving for t. When I plug in the given information, I find out that I end up getting 700 equals 400 e raised 0.02t. Upon simplification, I end up getting 7 over 4 equals e raised 0.02t. Now, that is an exponential equation. And how do we solve an exponential equation? We take log on both sides. Since the base is e, I take natural logarithm on both sides. By taking natural logarithm on both sides and using the power rule, the 0.02t comes out to the front, and we have natural logarithm of e, but natural logarithm of e is just 1. So 0.02t would be equal to natural logarithm of 7 over 4, and by dividing 0.02 on both sides, we could solve for t as 27.98, which gives us a value, approximate value of 28 hours. So if you started with 400 bacteria, we'll expect to have 700 bacteria at 28 hours. Having seen applications on exponential equations, here is one on logarithmic equations. This is commonly used in chemistry. We all know pH. pH determines the acidity of the solution. If pH is 7, the solution is neutral. If pH is less than 7, the solution is acidic, and if it's greater than 7, the solution is basic. The formula for pH is equal to negative log of H3O plus, which is the hydronium ion concentration in moles per liter. Here is the first example. Suppose the concentration is given for a solution, and it turns out to be 0.0027. What is the pH of the solution? This problem just requires you to plug in the given concentration in the formula. So I take 0.0027, plug it here in the formula for H3O plus concentration. I find the answer to be 2.5686, which makes the solution acidic. The second example, suppose you have an aqueous solution, you have a pH as 8.22, and you want to find the concentration. We know the value of pH, which is 8.22, and I know the concentration. I don't know the concentration. I'm trying to find the concentration, so I have to solve for H3O plus. By multiplying by -1 on both sides, I end up getting minus 8.22 equals log H3O plus. Now that is a logarithmic equation, and we know how to solve a logarithmic equation. We take the power of 10 on both sides because it is a base 10 equation. So raising both sides to the power of 10, exponentiating the power of 10 on both sides, we end up getting 10 raised minus 8.22 equals 10 raised log H3O plus concentration. The 10 and log base 10 would vanish because they are inverses of each other. That gives us H3O plus to be equal to 10 raised minus 8.22, which would result in an answer of 6.85 times 10 raised negative 9 m. So that is the concentration corresponding to a pH of 8.22. So these are some applications of exponential and logarithmic functions. Of course, there are many more applications, but to just understand exponential and logarithmic functions, these basic applications are quite sufficient. I hope you understood these applications. Thank you for watching the video.